When Windows NT 3.5 was released in 1994, it brought something huge to the PC ecosystem: native support for OpenGL. Microsoft needed a way to demonstrate this technology to users who probably didn't even have dedicated 3D accelerator cards. 3D pipes, along with 3D maze and 3D text, were built specifically to show off the OpenGL rasterizer. It proved that the operating system could take 3D vertices, project them into two-dimensional triangles, calculate lighting normals, and draw them to the screen in real time. It was a massive technological flex. This was the absolute peak of the computer world in the 90s. How much time did you spend staring at the Windows 3D Pipes screensaver? Feel free to ask the same question to your parents. We like interesting graphics projects here, so let's get nerdy and recreate it in a slightly different way. We are not going to use OpenGL and we are not going to touch the GPU directly. In fact, we are not even going to draw a single 3D triangle. We did all of this before with DirectX though. By the way, even Microsoft ported it to DirectX later on in Windows XP. Instead, we are going to dive into low-level computer science and build this with pure math from scratch, using rays. For every single pixel on the screen, we will shoot a mathematical ray into void and calculate exactly where it intersects with a perfect sphere or cylinder. Easy. To start, we just need a blank canvas. I will use the lightweight C++ pixel game engine as many times before. You will find links to the repo in the description. Here is the absolute baseline code to initialize our application and open a window. Notice we are setting the resolution to 320 by 240. It will help us with the old school pixelated look, which somehow looks more old school and pixelated than the original version, but I like it. Feel free to use any setting you want in your version. Here's our starting point. So how do we draw a pipe joint for the GPU? In OpenGL, or really just in 3D rendering in general, a sphere is actually made of plenty of tiny flat triangles. But since we are writing a raycaster, a sphere is beautifully simple. It is just two variables, a center point in a 3D space and radius. To draw it, we figure out roughly which pixels on our 2D screen the sphere might cover. We do this by projecting a two-dimensional bounding box. This is a crucial optimization, so we are not crunching heavy math for empty black space, where we know there is nothing. Then, for each of those pixels, we shoot a ray forward from the camera into the z-axis. To find out if this ray hits our sphere, we use the analytic ray-sphere intersection formula. It boils down to a classic quadratic equation. If the determinant is greater than or equal to 0, our ray hit the sphere. If we were to continue and trace the rays after the hit, we would get a ray tracer. But no, not this time. We stay with just one hit, and this is Raycaster. Do you know how Wolfenstein 3D worked? That's right, exactly like this. If we stop there and just color the pixel green, we get a flat two-dimensional circle. To make it look 3D, we need lighting. Because we know the exact point in space where our ray hit the sphere, we can easily find the surface normal just by subtracting the sphere's center from that hit point. Once we have the normal vector, we calculate the dot product between it and our light direction. That gives us our diffuse shading. I can vividly remember that the pipes were shiny. It got a kinda smooth, plasticky vibe. Well, it doesn't look like that in the videos I found. See how basic it is? Nah, I'm going to believe my definitely correct memory and draw the pipes with highlights. Technically, we call it a spectral highlight, and we achieve this by taking the dot product and raising it to a very high power, something like 35. This concentrates the light reflection into a sharp, glossy point. Here is the code to render our very first glossy pipe joint. Notice how the entire shading model is just a few lines of math inside the intersection check. Let's talk about the straight segments. Mathematically, that means we need to intersect our ray with a 3D cylinder. If it is confusing to you, just imagine that we operate in complete darkness. There is something, the pipe structure in this case, but we cannot see it. In the computer world, it exists because it is defined. But to actually see this, we need light. Rays flying into the scene and actually reflecting from the pipes. It is the same in reality. We are able to see things just because light bounces from them to our eyes. A cylinder is defined by 2 points in space and a radius. Ray-cylinder intersection is a bit more complex than a sphere. We have to use cross products to find the relationship between the ray vector and the cylinder's central axis vector. We solve another quadratic equation, but this time, if we get a hit, we are not done. An infinite cylinder goes on forever. We have to project that hit point back onto the central axis to check if it actually falls between our start and end points. If it does, we calculate the normal and light it up. Feel free to pause for the math. You can check other videos on my channel with the topic of raycasting and ray tracing, where we talk about it in more details. As soon as we introduce multiple objects, like 2 joints and a segment, we hit a wall, overlapping. If a pipe in the background is drawn after a pipe in the foreground, it will paint right over it. To fix this, we need a beautiful piece of computer graphics tech, a Z-buffer, depth buffer. We cannot reliably use something simple like the painter's algorithm, because you might have a pipe in front of pipes and behind other pipes at the same time. We allocate a one-dimensional array of floats exactly the size of our screen. Every time our raycast calculates a hit, we look at the distance to that hit, which is our t variable. Before we draw the pixel, we check the Z-buffer. If our new distance is smaller than the value stored in the buffer, it means this object is the closest thing to the camera so far. We draw the pixel and override the Z-buffer with the new closer distance. If it is larger, the object is blocked by something else, so we simply skip drawing it. That's how the original OpenGL implementation works, by the way. Let's add the depth buffer to our engine, write the cylinder intersection math and connect 2 joints. I will place one joint slightly closer to the camera to prove that depth buffer is doing its job perfectly. Alright, we have a solid rendering pipeline for our geometry, but right now we are just staring straight down the Z-axis. To capture that authentic screensaver aesthetic, we need a classic isometric perspective. We also need a space for our pipes to actually exist in. Because we bypassed OpenGL entirely, we do not have a built-in view matrix. We have to do the camera transformations ourselves using trigonometry. For every point in our 3D world, we need to rotate it on the y-axis to change our heading and the x-axis to change our pitch. We calculate the sine and cosine of our chosen camera angles and multiply them against our world coordinates. And finally, we push the result away from the camera by adding to the z distance so we can see the whole structure. The original animation did not always touch the camera, so feel free to tune it as you wish. I just wanted to add a variable there. And now the big question. How do the pipes know where to go without crossing each other? The secret is an invisible 3-dimensional grid. The pipes don't move freely through space. They grow from voxel to voxel while keeping track of which spaces are already occupied. It's basically a tiny voxel engine. A voxel is a discrete element in a 3D grid. You can imagine it as a cube, even like a pixel, but in 3D. We will define an 18 by 18 by 18 Boolean array in memory. If a grid cell is false, it is empty. If it's true, a pipe is occupying it. To test this, we can pick a random starting point in this grid, choose a random direction and keep adding segments in a loop until we hit a wall or our own pipe. We take those grid coordinates, multiply them by a spacing value to convert them to 3D world space, pass them through our new camera transformation, and hand them off to our raycaster. Let us put this together. In this runnable code, we generate the static multi-cloud pipes the moment the program starts, and we view it through our new mathematical isometric camera. We have the rendering, the camera, and the voxel grid. Now we need to solve the simulation. We need to make it move, and we need it to behave exactly like it did back in the 90s. If you watch the original Screensaver closely, the pipes don't choose a completely new direction at every step. They have a preference for continuing in that direction, if possible. When they do change direction, they choose another axis-aligned direction on the 3D grid. And every move is checked against the grid, so a pipe can't enter a cell that's already occupied. If it's forced to turn, it scans the available adjacent voxels in our 18 by 18 by 18 grid. If all paths are blocked, the pipe is dead. It drops the final sphere to cap off the dead end and stops moving. But we cannot just instantly pop the geometry from one grid cell to the next. It has to go smoothly. To do this, we introduce an active pipe structure that tracks a progress variable from 0 to 1. Every frame, we draw a cylinder stretching from the last joint to the current progress point. There is a visual catch here. Our cylinders are hollow. If we just render a growing cylinder, the camera will see right down the inside of the tube. The trick is to draw a temporary sphere right at the growing tip, moving along with the progress. It acts as a sliding cap. Once the progress hits 1, we lock that completed segment into our static arrays, update our grid coordinates, and calculate the next move. Let us wrap this into a simulation loop, spawn a few pipes simultaneously, and add a restart timer that resets the grid when all pipes get wrapped. Here is the final complete C++ engine code. Compile this and you have a mathematically pure Z-buffered software Raycaster running a recreation of the classic 3D pipes. And there we have it. We took a blank 320 by 240 canvas and transformed it into a 3D Raycaster. No OpenGL, no GPU acceleration, just the raw CPU power, crunching ray sphere and ray cylinder intersections for every single pixel to emulate the old Windows feeling. If you want to play around with this, try tweaking the camera angles, adjusting the field of view, or altering the grid size. As a small bonus experiment, try modifying the lighting. The code we wrote gave us a highly reflective, glossy plastic look. If you want to see how much of a difference the specular highlight makes, swap out the compute lighting function with this matte version. It removes the high power exponent and softens the ambient light, completely changing the aesthetic from shiny plastic to a soft clay-like material. You can check out this video if you want to see more about raycasters in computer graphics and games. Thanks for watching. Like, comment, subscribe, and if you really like what you saw, consider supporting the channel via membership. See you next time, and ciao!